Hello, my name is Dafydd Ravenscroft. I'm going to be presenting a brief overview of my poster presentation for FLEPS 2021 entitled A Wearable Graphene Strain Gauge Sensor with Haptic Feedback for Silent Communication. This is something our group, the Occhipinti group at the University of Cambridge, has been working on recently. So, as a quick overview, first of all, what is the problem we want to address? So speech impairments are a common and wide-reaching problem which affect millions of people worldwide. Silent communication is the method by which you can convert silent attempts to speak into speech. An example of this would be lip reading, when the listener uses visual information rather than audio information to understand what the person is saying. Being able to perform this silent communication is particularly useful for people who have lost their ability to speak. So what we have done is we've designed a wearable strain sensor which can be attached to the throat. This detects small movements when someone speaks or attempts to speak as changes in the resistance of the device. These are then passed to a machine learning algorithm which makes predictions on what is being said, with feedback then passed to the wearer to inform them if the speech has been correctly predicted. So this is a device which should be highly useful for those with speech issues, and we're going to demonstrate a proof of concept we've developed here. So our methodology can be broken down into three main stages. So firstly, the fabrication of the device, in which we screen print graphene oxide onto lycra. Then the data generation, in which we produce some data sets with a set of predefined words. And then thirdly, classification, an algorithm was developed and trained on the generated dataset. It was then tested to see what prediction accuracy could be achieved. So the fabrication process was relatively simple. So graphene oxide ink was screen printed onto lycra fabric. This was dried and repeated to ensure full covering was made, with this then cut to size and proper electrodes added with silver paste. So this method, as well as being simple, produced a flexible, close-fitting and wearable sensor which exploited the high gauge factor of the graphene oxide. So we developed two distinct data sets to allow us to provide quantitative analysis of the performance. The first was a movements data set. This consisted of nodding, coughing, yawning and swallowing. The second was a word data set. This consisted of a set of 15 monosyllabic words selected from a phonetically balanced list of words. This allows for the distinguishment of different sounds commonly used in the English language. And so two participants each contributed 10 samples for each of the individual words and movements. So we wanted to use neural networks for the classification for this approach. So neural networks are a branch of machine learning which have shown great success in pattern recognition, signal processing, and classification problems. So they combine feature representation learning and supervised discrimination into a uniform end-to-end training framework. This enables important features to be discovered within the data and then used for classification. So we developed an architecture combining two types of layers called convolutional layers and LSTM layers. And so this combination allows us to be able to detect both pertinent local features and also pertinent temporal features. So the generated data is split into two data sets, one for training the algorithm and then one for testing the prediction accuracy of the algorithm. So the developed strain gauge showed some promising characteristics. We had a predictable resistance response up to 32% stretch of the device. We had a gauge factor of up to 35, and it also showed stability as well as wearability. So the prediction algorithm has produced some very promising results with an accuracy of 82% in the 4-class movement set and a 51% prediction accuracy in the 15-class word set. And there are some examples of some of the resistance readings we got from the device. So another aspect which we are interested in is the use of haptic feedback to inform the user if the word has been successfully predicted. So we want this haptic feedback to be incorporated into a patch alongside the sensor device with high wearability. So obviously feedback is necessary in silent communication devices, and providing it haptically is particularly useful for those with hearing difficulties. So by thresholding the prediction probabilities, which is something you can do with neural networks, we can decide if the algorithm is confident in its prediction, and if it's unsure, it can feed this back to the user. And this will allow the user to adapt their speech and improve the accuracy of the device over time. And we're currently looking into a number of different approaches to incorporate this into the patch. So that's a very quick overview of the project. So we've summarized, we've kind of developed a proof of concept method for silent communication, consisting of a wearable strain sensor and a machine learning algorithm to allow predictions on our developed movement and word datasets. We demonstrated 85% and 55% prediction accuracies respectively on these datasets, and this demonstrates the potential capability of our approach, and we've identified a way to take the project further as well. So thank you for listening. I hope you enjoyed the presentation, even if it's very quick. If you're interested, please come and find our poster at the conference. Thank you.